Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all my lectures. Now, I have an original lecture series on data analytics and geostatistics. I'm starting to re-record some of the lectures. I've made improvements on the notes. I have better gear now, and I thought it'd be nice to do a little bit of a refresh. So let's talk about statistical expectation. Now, before you cover this lecture, you should cover the lectures on statistics, univariate statistics, probability, in order to be able to follow along with this. All right, so what is statistical expectation? The easiest way to describe it is a probability-weighted average of a discrete or continuous distribution. Now, for the discrete distribution, it's actually very straightforward. Imagine a normalized histogram. So we have a histogram over here. Now it could be an actual categorical variable which only has classes 1, 2, 3, and 4 that are ordinal. They have some type of a ordering relationship. So it could make sense to calculate an expectation of them. Or it could be a continuous property like this distribution shown right here, where we have a continuous range of possible outcomes, but we have a normalized histogram. We binned up the range of possible values, and now we have these bars, and each one of them represent the probability of being within each one of these intervals, equal-sized intervals along the range of possible values. In order to calculate the expectation in this case, all we have to do is take the summation of the values multiplied by that PDF value, or the probability if we're just talking about normalized histogram. So this is it. This is all we have to do, is just go ahead and take the summation of the values. And usually the values will be the specific categories or the centroids of the bins multiplied by the probability of being within each one of those bins. So this value right here in the centroid multiplied by that probability, this value here by that probability, and so forth. And we would expect by closure that the sum of all of these densities, or these values, these probabilities, in fact, in the case of discrete or normalized histograms, should equal to 1 closure. All possible outcomes, 100%. Now, for a continuous variable, we can do the same thing. All we do is now we're working with a continuous PDF. And so we have a continuous line that is a measure of density across all possible values from the minimum to the maximum. And what we can do, this is actually really cool, is we can do the integration from negative infinity to positive infinity of the value multiplied by its density, which are really a measure relative likelihood. Now, we would do this and we'd have the same closure constraint. Instead, in this case, we could state that the integration from negative infinity to infinity of the PDF itself, the density values, should have a area under the curve or equal to 1. In other words, all possibilities is equal to 100%. So this is how we calculate an expectation, a probability-weighted average of a discrete or continuous distribution. Now, you might be sitting back there thinking to yourself, well, this just sounds like the arithmetic average. How is it different? And let's draw some parallels between them. The expected value for a random variable is the long run, and when we say long run, we're always assuming enough samples. They're average. So in other words, they are the same thing. If we had not the distribution as shown here, but instead I had enough samples from the distribution, and I just calculate the average of them, that should be equal to the expectation, assuming I have enough samples. Now, what else do we have to assume? Well, we'll assume random sampling. In other words, representative sampling, equal probable. All samples have equal probability of being sampled or drawn from the distribution. The unbiasedness from the fact that we don't have a bias, we're not sampling one part of the distribution more than another. It's all equal probable, and we have a large enough sample set, so we have a good stable result. It's enough to be able to get a good grapple on the expectation. And so let's say we have enough samples. Now I know 10 is not a lot of samples, but I got lazy. I didn't want to draw a lot of values here. But imagine I have a sample set that we say is equal probable, unbiased, and large enough, and their porosity values drawn at random from A distribution. If we assume they're all equal probable, that would mean the probability values for index 1 through 10 is just equal to 1 over n. And so we could go ahead and calculate the expectation. Using our equation that we showed on the previous slide, it would look like this. It would just be the summation of the values multiplied by their associated probabilities. We could substitute 1 over n for the probability. That's a constant, so we can pull it out of the summation, put it in the front, and what do we have? This is in fact the definition for the sample arithmetic average. So they really are the same thing if we have enough samples available and they're representative. But let's go ahead and we can give ourselves a very simple example based on what we just explained around discrete distributions. This is an ordinal discrete distribution or categorical ordinal, where we have a really nice simple ordering relationship. We've just binned grain size into discrete bins. So the following grain sizes in millimeters are available to us from some type of a soil or crushed rock sample, or maybe a non-crushed rock sample. And so we have 10 millimeters with 10% probability, 20 millimeters with 50%, all the way up to pretty large size here, 50 millimeter with a 10% probability. Calculate the expected grain size. Now, how would you do that? Now, go ahead, pause me, figure this out, and I'll keep going in 3, 2, 1, and let's go. Not a big deal, right? All we had to do was take the summation of the probability for each one of those bins or discrete outcomes, 10% for 10 millimeter, 50% for 20 millimeter, and all the way across, and we will get the expectation. Now it's 27 millimeters in expectation. Now, I hope you can see intuitively that these probabilities must sum to 1, or we would create a bias. Imagine if they were to be a sum to a very small number, well, you would have an expectation to be very small. It wouldn't make sense. Now, there's a lot more we could talk about with regard to expectation. And this is where the power is, because everything we talked about so far, what have I said? It's the arithmetic average if we have enough samples. And I showed you a really simple example with probability, effectively probability weighting of bins, but there's so much more you can do with expectation. It's a beautiful linear operator. And so a lot of cool things happen. First of all, the expectation of a constant, the expected value of this constant is equal to the constant. Now that makes sense. A constant is not a random variable. There's not multiple possible outcomes. It can only be one value. So that makes perfect sense. The expectation of a random variable plus a constant, well, the expectation of x, capital X, random variable, plus a constant, it has a distributive property, our expectation. So we can pull the two parts apart. So we get the expectation of the random variable x plus the expectation of the constant. Expectation of a constant is a constant. And so the result is the expectation of a random variable plus a constant is just equal to the expectation of the random variable, and then just add the constant in. The expectation of a product of a random variable and a constant, well, look at it. We can just go ahead and take the constant value and pull it out, put it in the front. And so the expectation of a constant times the random variable is just the constant times the expectation of the random variable. Very, very helpful. Now, if we have two separate random variables, notice that x and y are both capitals here. Then, while we have the distributive property again, we can pull them apart and we just deal with the expectation of x plus the expectation of y. Very, very easy. Now, the product of two random variables is a little bit more complicated, but simple if we can deem that they are independent of each other. The expectation of x times y, note they're both random variables, if we assume independence between them, is equal to the expectation of x times the expectation of y. Okay, so these are some basic operators with expectation that we can use to solve a wide range of problems. So let's go ahead, let's try some problems out. Just some really, really simple ones just to get some ideas, and then we'll end with a more complicated one that'll be a bit more difficult. Okay, so I'll state the problem, and you can go ahead and pause me and work it out. All right. The expected total porosity is 16%, but you expect that, I should say that you estimate that there should be a reduction by about a constant of about 3% to all of these total porosity samples to get them to an effective porosity. So you've deemed that you just need to subtract a little bit of porosity because it's not really connected, it's foggy, it's not forming nice paths for flow. So we have the effective porosity is equal to the total porosity minus the constant. The expected total porosity is 16%. The constant is 3%. Now calculate the effective porosity. And so what's the problem? What's the expected effective porosity? This is the equation for it. Okay, go ahead, pause me. I'll give the answer in 3, 2, and 1. Well, that's very straightforward. We already worked through that just now. We have the distributive property of expectation. We can go ahead and say the expected value of total porosity minus this constant to adjust it to effective porosity. It's just equal to the expectation of total porosity minus the expectation of the constant. Well, the expectation of a constant is equal to the constant, and so we get the expectation total porosity 16% minus the constant and 13%. Now, if you think about it, just think about an arithmetic average. If I had an average of 16% for a whole sample set, I was to go ahead and subtract 3% from every one of the samples. It makes perfect sense, just thinking about the equation of averages, that it would just be sliding the average by 3% lower to 13%. Okay, let's look at this one. The expected absolute permeability is 100 millidarcies, and the relative permeability due to having multiple fluids, multiple phases involved, is 0.25. Calculate the expected effective permeability for the reservoir. So the equation for effective permeability for the specific phase is equal to the relative permeability multiplied by absolute permeability with this equation right here. We know the expected absolute permeability is 100 millidarcies, and the relative permeability is 0.25. How would you solve this? All right, I'll give you time to work it out. 3, 2, 1, here's the solution. All right, so not a problem again, because we're trying to solve for the effective permeability for that phase. We have a constant times the random variable, the absolute permeability, for which we have a bunch of samples from the reservoir. We can take the constant out to the front, and we can say our equation is now the relative permeability times the expected absolute permeability. And so the result is 0.25 times 100 millidarcies, and we get 25 millidarcies. Not a big deal, but really cool, because if you understand expectation, you can do a lot of calculations on the back of an envelope. Very quickly get a calculation. That was my dog. That scared me. Okay, so here's another one, a little bit more complicated, but we'll use the concept of independence to be able to solve this very easily. Given random variables, and remember, random variables, reminder, they're features that are uncertain with a range of possible outcomes. From a water reservoir, and we have the expected porosity of our water reservoir is 15%. The expected area is, we have a distribution of uncertainty for area. That makes sense. About 1 million square meters. About a kilometer by kilometer reservoir, that makes sense. Expected thickness, there's some uncertainty in that, about 100 meters. And the saturation, well, we're just going to say it's 1.0. We'll just say probably that should have been a constant. And it's water. There's no other phase here. It's all water. Okay. So we need to calculate the expected water volume, because we need to that for some type of decision making with regard to this water reservoir, what's going on with it. So the equation for the volume of water is the porosity times the area times the thickness times the saturation of water. Okay, this is the pore space, and this is what fraction of the pore space is full of water. Very easy. We need to calculate the expected value of the volume of water. So we're going to get the expected value of this equation. All right, so go ahead. Now assume independence. I should state that again, and go ahead and solve this in 3, 2, 1. Okay, so what do? Not a big deal again, because if we assume independence of the porosity, area, thickness, and saturation water, we can pull them all apart and just take the product, the expected value of the porosity, the expected value of the area, times the expected value of the thickness, times the expected value of the saturation water. and we can multiply them all together, and we get 15 million cubic meters of water available in our reservoir. Okay, pretty straightforward stuff. Kind of nice, simple examples of expectation. Now here's a tougher one. Let's work through this one together. Now, when we talked about the definition of variance, we suggested that it was the average squared difference between the values in the sample set minus the average. Now, if you look at this, the expected value is a probability weighted average, and the expected value of x is simply going to be the average of the data set, and this is the square of it. So effectively, I hope I can convince you that this equation is the same as our definition of variance, but in notation of expected value. Now, what's very interesting is that we can re-express this equation of variance and expectation with this equation right here. The expected value of the squares of all the values minus the square of the expected value. It's kind of a beautiful symmetry. The most important thing about this equation, if you look at it, the first equation, I had to calculate the expected value of the distribution, or the samples first, the average of the samples first, in order to calculate this equation. It requires 2 passes of the data. This one right here, I actually don't need to do that in 2 separate passes. I can have 1 pass of the data in which I'm calculating the square of the variable and then get its expectation, and taking the values and just getting the expectation of it, and then simply at the end treat that like a constant to subtract the square of that. I can do this calculation with 1 loop, 1 pass of my data set. So, kind of interesting. Let's go ahead and prove that this works using expectation and all we've learned about it. Now, I'm going to give you some hints. These are what we're going to need to know from what we already covered. Now remember, the expectation of a expectation is just an expectation. You see that? Effectively what we're saying is the average of an average is an average. Okay? That's the first thing you have to remember, because that's going to come up. And remember this rule right here. If you have the expectation of a constant times a random variable, it's simply the constant times the expectation of the random variable. And right here, the distributive property, if we have the expectation of x squared plus 2x, it's equal to the expectation of x squared plus the 2 times the expectation of x. We can pull the 2 up front. We have the distributive property for these 2 terms. Okay, so let's go ahead and solve this. The first thing we're going to do is we're going to take the quadratic and expand it. Okay, so we start with the expectation of x minus expectation of x squared, and we can take that entire thing and expand it out. Not a big deal. So if we take these terms and we expand them out, we simply get the expectation of x squared minus 2 times x, expectation of x, plus the square of the expectation of x. Now, let's go ahead and make some adjustments right here. First of all, the first thing we can do is remember, if we have all of these separate terms all to the expectation, we can just simply pull them all apart. So we have the expectation x squared minus these other terms. Well, that's just expectation of x squared minus this part, expectation of that. Now remember, 2 is just a constant, so we'll pull the 2 out in front right off the bat. And then we'll have the expectation of this term, which is the square of the expectation of x. Okay, so we've separated out all of the terms. Now what can we do? Now the first thing we should notice is that what we have here is the expectation of x times expectation of x, all within expectation. Now this expectation of x is already going to be a constant. So we can just pull that right out of this expectation, and so we get minus 2 times the expectation of x times the expectation of x. Now the same thing happens here. This expectation of x squared is effectively a constant also, and so the expectation of a constant is just equal to the constant, and so we can pull this term out right here too. Okay, so we're good to go. Now the next thing that's going to happen is we're going to realize, and I realize I'm missing a bracket there, but anyway, the next thing you can realize is that if you have the expectation of x times the expectation of x, that's simply equal to the expectation of x squared. So we have expectation of x squared minus 2 times the square of the expectation plus the square of the expectation. Now, if you look at it very quickly, you can see that you can have 2 minus 2 here, you have plus 1 here. We can simply simplify that to say the variance is equal to the expectation of x squared minus the square of the expectation, which is what we had up here. And therefore, we've proved it, that we can do one loop and calculate a variance. So that's really nice. That's a nice little proof because it forces us or gives us the opportunity to use many of the concepts of expectation to complete it. So a great practice. Now, why is it important to know about expectation? Well, expectation is widely used for decision making. For instance, many times decisions are made based on maximizing project expected net present value. Now, it also provides powerful methods to work with expectation-based problems. If you understand how expectation works, you can combine different features together and go ahead and calculate, often on the back of an envelope, expected value for resource in place, water in the subsurface, whatever it might be. And many theoretical developments in data analytics and geostatistics are based on expectation. When we derive these simple kriging, ordinary kriging systems later on, we'll specifically work in expectation, and it'll be beautiful. I promise you it'll be beautiful the way it's going to all fit together. All right, so that is all I was going to talk about as far as expectation, statistical expectation. I hope this was useful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I teach and work and conduct research in data analytics, geostatistics, and machine learning. I'm happy to discuss anytime. I'm on Twitter. I'm on GitHub. What else? YouTube channel, of course. All right, take care.